Welcome back to Lab 2A, where we will continue building our solid modeling skills in Autodesk Inventor. In Lab 1B, we gave a whirlwind tour of the Inventor part modeling interface and the general steps for part modeling, which included sketching 2D profiles and using Inventor's 3D Create tools. We also introduced some of Inventor's 3D Modify tools, Fillet, Chamfer, and Hole, and we will get more practice with these in our Lab 2 examples. In this video, we will introduce some more tools at our disposal, namely the 3D tools Sweep and Loft, the 3D Modify tools Thread, Shell, and Hole, which we already introduced in the last video, and some handy 3D pattern tools. As with the Lab 1 video, 2 examples will be walked through in accompanying videos, where we will also talk about some solid modeling best practices. Before we get into new tools, let's review the general part modeling steps one more time, as this is super important. The first step is, of course, to open up a new part file, making sure we choose a template in the correct units, and then creating our part one feature at a time. Making these features involves creating a 2D sketch on some plane, fully constraining that sketch, and then bringing it into 3 dimensions using one of the 3D modeling tools at our disposal. Last lab we got some practice with these steps, and this lab we will build on that with some more complex examples. These examples involve part modeling from multi-view drawings, so it is also important to be able to read multi-view drawings and understand the symbols and conventions used to indicate part geometry. This includes symbols like phi and r for diameter and radius, TYP for typical dimensions that appear in multiple places on the part unless specified otherwise, and the times sign to indicate the number of times a feature appears on a part. There's also quite a bit of notation associated with threaded and countersunk or counterbore holes, as shown in these example drawings to the right, and we will practice some of these examples by generating holes from these annotations. Before we get to holes, let's start off by introducing some additional 3D Create tools. In the last lab, we learned about extrude, revolve, and rib, but there are quite a few more tools to introduce. One of these is the Loft tool, which allows you to generate a 3D profile from 2 or more sketches, where you select the sketches and the tool generates a smooth transition from one sketch to another. This could involve numerous sketches, like for this hammerhead, or it could be as simple as generating a 3D loft profile from a square to a circle. Some additional options are to specify rails to define the transition from one sketch to the next, as shown in this example, which allows us to generate some pretty neat geometries. Another 3D Create tool is a Sweep tool, which is like a more general form of the Extrude tool. The Extrude tool allows us to sweep out a 2D profile in a straight line normal to the 2D profile's plane, but the Sweep tool allows us to specify any path we want to generate a 3D feature. Here, the Sweep tool is used to make the slide feature, and another example is extruding a circular profile along this path to produce a hitch pin. It should be noted that just like the extrude and revolve tools, the loft and sweep tools can be used in join or cut mode to either add or take away material from a part, respectively. Now that we've covered these 5 main tools from the 3D Create panel, let's move to the 3D Modify panel. Last week we saw some examples where the fillet and hole tools were used, but we stuck with simple through holes in our examples. In reality, we could easily use the extrude tool to make these constant diameter holes rather than the hole tool, but the hole tool does particularly come in handy when we start talking about more complex hole geometries, like blind holes that don't go all the way through a part and they have a tapered end as a result of drilling. Other hole features include a counterbore, spot face, or countersink to allow the screw to sit flush with or below the part surface, as well as threads. If a hole has threads, we call it a tapped hole, and these threads give grip for screws to stay in place. So let's look at some examples of using the hole tool to make more complex holes. In this example, which we will assume to be in millimeters, we can read the multi-view hole annotation as follows. The 3 times means we have 3 holes. Phi 6 through means they have a diameter of 6 millimeters going all the way through the part. And the rectangle-like symbol indicates a counterbore that has a diameter of 10 millimeters, and the arrow 3 tells us that the counterbore has a depth of 3 millimeters. Finally, the M6 is an indication of an M6 thread on the holes for the 6 millimeter diameter portion. We can see the threads in the multi-view drawings as the dashed lines surrounding the inner hole diameter, and once modeled in Inventor, these holes would look like this. So let's walk through how to generate these holes using the hole tool. In the last lab lesson, we made a sketch with points to indicate our hole locations, but we could also dimension the hole locations on a planar surface directly with the hole tool without having to make a sketch beforehand. When I select hole, I can click on the general location of the hole, and then I can specify its center point by indicating its distance from the surface edges, like so. Once the hole position is set, I can then specify the hole type, the threads, and behavior in the hole tool dialog box. So we want to select tapped and counterbore for this hole type, and for threads, since we are working in the metric system, we want to select the ANSI metric M profile for thread type, and we want size 6 threads based on the M6 specification. Unless it is specified otherwise, we will assume coarse pitch threads for this course, where pitch refers to the distance between threads. So we will just select the largest pitch designation in the drop-down. In this course, we will just leave the class and direction as is, and since we want the threads to go the full distance of the hole, we can check off the full depth checkbox. Finally, in the behavior section, we can indicate our counterbore diameter and depth, and there we have our holes. Here's another example in the imperial system, so we are working in inches here. From this multi-view annotation, we read that we have 3 half-inch diameter holes that go all the way through the part, and this V tells us that the holes are countersunk with a countersink diameter of 0.75 inches and a countersink angle of 82 degrees. Finally, these holes have a half-13 UNC thread designation, which means that the threads are for half-inch holes with a pitch of 13 threads per inch, which you might be able to count out in the isometric pictorial of this example. The process of making these holes is much the same, but now we are specifying a countersink seat, and our thread type changes to ANSI unified screw threads for the imperial thread system. We again set our thread size and designation according to the hole dimensions we were given. These holes and the threading still go all the way through, so we select full depth through all termination. And then in the behavior section, we get to set the countersink diameter and angle. So these two examples hopefully give you a good grasp on the hole tool. And again, they have demonstrated that you don't necessarily need a point sketch beforehand to make a hole. You can dimension the hole position from the edges of a surface, as in these examples, or you can make a hole concentric on a round feature or a circular feature by selecting that circular edge, which can be handy. One thing to note is that you do need a planar surface to define a hole feature, so if you're trying to place a hole on a curved surface, as seen here, you may have to define a new sketch plane tangent to the surface and sketch a point on that plane in order to make a hole. So that is something important to remember when you are using the hole tool. Another 3D modify tool is the thread tool that allows us to apply external or internal threads to cylindrical features. And yes, these threads have the same standards and designations as we saw in the hole examples. So there is not much new to cover with this tool. You simply select a cylindrical surface and specify the thread designation as we did for the holes. The shell tool is another interesting modify tool that allows us to hollow out parts to a specified wall thickness, as shown for this curved pipe. You just have to select the faces to remove and set the thickness, and there you have it. Consider our first example in Lab 1 where we had a hollowed out box. In that example we used the extrude tool to hollow it out, but we could have easily used the shell tool instead to save ourselves from having to make a sketch. So that covers our main modify tools. Now let's move on to some of our pattern tools. As the name suggests, the pattern tools enable us to repeat features in particular patterns, which can save us a lot of time and effort for parts displaying symmetry. We will look at some examples of rectangular and circular pattern tools now, and we will use the mirror tool in our second part modeling example. So to start, the circular pattern tool copies solid features of an object in a radial fashion about an axis. To use this tool, we need to have our feature that we want repeated, as well as the axis that we want the feature repeated about. So the first step is to make sure that that axis is visible. Then we can select our circular pattern tool, select the feature to be repeated, and once we have that complete, we can click the rotation axis button and choose our axis of rotation on the model. Then we can specify our pattern placement, including the number of repeats, and the total rotation angle about which we want the repeats to be placed. In this example, we're copying whole features, but this could be any type of feature. The rectangular pattern tool is very similar, but it allows us to copy solid features of an object in a bidirectional or linear fashion instead. So for this tool, we first select our feature to be repeated, and instead of selecting an axis of rotation, we select pattern directions. So we click direction 1 and choose an edge to represent that direction. And once that's complete, we can specify the number of repeats and their spacing in that direction. We then repeat the process in direction 2, which allows us to create a sort of matrix of features in a rectangular pattern. It is important to note the direction of the arrows on the edges that you select, as this will affect the direction of repetition, which you can switch by either clicking this flip direction button or by specifying a negative value for the spacing. As with the shell tool, we could have used this tool in our Lab 1 example 2 part to make the 4 holes on that part. Now that we've introduced a bunch more tools in Inventor, we will put some of these to use modeling 2 examples in accompanying videos. First this example, followed by this one, which is like a shell and tube heat exchanger casing. Now that we've become more familiar with Inventor, we will also start implementing some part modeling best practices. First, we will practice naming our part features in our model browser, which is analogous to documenting code. It makes it easier to understand a model and its constituent features. We will also talk about using geometric constraints rather than dimensions wherever possible in 2D sketches, as we will see that this makes updating part geometry much easier if revisions are required. As with Lab 1B, this slide provides some troubleshooting tips that you can consult on your own time if you run into any issues as you develop your part modeling skills in Inventor. And these are also provided in a PDF document with the rest of the course material for your perusal. For now, this wraps up our lab video on Inventor modeling tools. We have now introduced a number of create, modify, and pattern tools, and I encourage you to play around with these tools on your own to see what they can do. This lab lesson and the previous week's lesson gives you all the tools needed for the first part of Assignment 2, where you will model a part from an engineering drawing. However, for Assignment 2, you will also be required to recreate that drawing that you are given, and Lab Lesson 2B will give you the tools needed to do so.